Good afternoon, everybody. I am Swapnendu from IEEE Bhopal. Topic of my presentation is direct red patterning of flexible substrates using scanning probe-based electrolithography technique. The outline of the talk, we'll start a brief introduction of scanning probe lithography. Then we'll look into the phenomena of electroliquefaction of chrome films and some of the parameters that we can use to tune the electroliquefaction process. We'll look into the scanning probe-based electrolithography technique, the setup, experimental setup that was used for most of the studies that were presented, ELG on flexible substrates, and thereafter summary activity work. So, what is scanning probe lithography? Scanning probe lithography is basically a set of nanolithography techniques in which surface modification is carried out using a very fine tip, which helps to confine a physical process underneath this tip. The physical processes can be of various nature. However, one of the SPL techniques that stand out is the oxidation SPL technique, in which we bring we bias this probe negatively, bias it, and bring very close to the surface. The water molecules in the ambient condense to create a water bridge. The applied voltage helps to split the water molecules and thereafter oxidize the surface, and was first demonstrated on silicon substrates. Now, what is the advantage of oxidation SPL compared to other SPL techniques? Is that it's based on oxidation process. Various types of materials, including insulators, semiconductors, and metals, can be patterned. It produce the oxides, which form are usually very chemically and thermally stable. And since the requirement is only of a few holes, it helps to limit proximity effects a lot. So, what happens if we take a chromium thin film and electrically stress it with a pair of probes? Around the cathode, we see that there's a liquid material that starts to form, which spreads out, spread radially outwards, and can spread to 100 microns in radius or even to 200 microns. So we did a lot of material characterization techniques, including wet tests, FTI, and Raman, to find out that this material that is formed is basically the hydrous form of chromium trioxide. This is one SEM image, and therefore the liquid material is a result of a electrochemical reaction that takes place. The electrochemical reaction is given by this chemical equation. In the hydrous domain, the chromium oxide stays as chromate and dichromate ions. Now, chromium trioxide is the only chromium oxide which has a high solubility in water. Therefore, once this oxide region is formed, if we dip the sample in water, we can effectively etch the chrome layers off. Now, in all these cases, the cathode probe was kept fixed. Now, what if happens if we traverse the cathode probe according to our required design? We can obtain patterns on the chrome layer, and therefore, after dipping the sample in water, we can effectively electro etch the chrome layer. And this is what has given rise to the scanning probe based electrolithography technique. I'll come back more on it, but first, let's look into the factors that can help and can tune this rate of oxidation or the spread of this oxide region. So some of the tuning parameters, first, strength of the electric field or voltage, frequency if you are applying an AC signal, then the DC dip, the duty cycle, as well as the thickness of the chrome film. All of these are mostly affect the electrical are the electrical parameters. There is also the effect of relative humidity and temperature, the experimental temperature, and you can see how significantly both RH and temperature affect this oxidation process. So let's look into what electrolithography is. So basically, we electro etch the chrome layer, and thereafter we can easily transfer the patterns that is formed on the chrome layer by using lift-off. In a hydrous environment, repeatable patterns of up to 40 microns has been achieved, a best case of around 3 microns. All of these results are using micro scale tungsten probes. When we try to replicate the same things using a conductive AFM tips, we were able to obtain patterns of to 9 nanometer, and successfully we were able to transfer the patterns to a different material of around 40 nanometer in width. Now, what makes the electrolithography process quite unique is that it's a resistless patterning process. We do not need any resist. The development of the oxide region takes place in water for the easy development process. We are effectively etching the chrome layer that gives significant advantage in the entire device fabrication process flow. And as you can see, the material transfer process is also quite easy. Now, the experimental setup, most of the experiments, apart from the AFM ones, has been done in a custom-built electrical characterization probe station. It was initially intended for characterization of transistors, but yeah, we use this one. It's vacuum compatible. It's also fitted with a microscope and a camera, and these are some of the features of this characterization probe station. Now, we all of these previous results, the chrome layer was deposited either on a silicon substrate or on a SiO2 Si substrate. We tried to replicate the same thing by depositing chromium on a flexible substrate. We try to follow this process flow. This is just a schematic of the process that we tried. These are the sample parameters that sample description that we took. The chrome layer was thermally deposited 25 nanometer thick. The polymer was the Kapton layer and the mechanical support we used as a glass slide. Some of the demonstrative results. This is a circular region. You remove, dip the sample in water. You can see the oxide regions get removed. These are some circular regions arranged in form of triangle and a square or a rectangle. This is the effect of the dwell time, that is how long the cathode is fixed in that particular position. And this is the effect of instead of applying a constant voltage, what happens if we apply a constant current, because the oxidation process is an electrochemical process. So this shows the effect of constant current, and this is a camera image of the Kapton substrate after the mechanical support layer was removed. So to summarize the talk, electrolithography is a process in which we can selectively oxidize chrome films to create water-soluble chromium 6 oxides. Use the chromium 6 oxides can be easily removed using water. Therefore, it's a direct and resistless patterning on chromium thin films without using any resist or developer chemicals. So previously, all the work that was done was demonstrated on silicon or hard conventional substrates. For the first time, we demonstrated the same on flexible polymer substrates, and thereby we can use this process while fabricating flexible devices. Now, the future work, we are working heavily on it to develop a feedback control system so that we can transfer the CAD designs onto the substrates, and obviously thereafter fabricate devices and sensors using this technique. I'd like to thank my supervisor and my group members, the central facility, as well as the funding agencies for the support. Thank you.